How's everyone doing? I know it's cold and wet outside, so I'm sure you're all happy to be inside. All right, I do apologize for my voice if it cracks. I'm sorry. I'm just, it's that time of year. So, all right, so welcome to Astronomy on Tap. We have some awesome talks today, one by our very own AOT member. And we also have some really cool prizes to be won for trivia. I'll talk about that a little bit more during intermission, but definitely participate in trivia. If you have not yet, please go ahead and grab a raffle ticket from Alex in the back. We also have some cool stuff to give away if you win the raffle. And as always, make sure you guys are courteous, keep it down when the presenters are speaking. During our Q&A, we are going to have a virtual talk, be our first talk. So if you do have questions, we're gonna ask that you go and speak into the microphone in the back so our online presenter can hear your question. For our second talk, it will be just normal, so you don't have to worry about that as well. All right, so for our first talk, we have Erin. She is currently a third-year biochemistry PhD student in the Department of Biological Sciences at LSU. The topic of her current research is transcription and the control of virulence in bacteria pathogens. She also has past experience in the realm of DNA damage and repair. So some fun facts about her: she shares a birthday with Harry Potter. She grew up playing Pokemon on the Nintendo Game Boy Advance, and at one time she was able to play 5 instruments. So give it up for Erin.
Hello. Can everyone hear me?
Yeah, we can hear you. Can you hear us? I don't think she can hear us. We can.
Can you guys hear? Okay. Thanks everyone for coming out. Today I'm gonna talk to you guys about bacteria in space. So we'll go over why life usually can't survive in space. Bacteria that can survive in space. How they do that, and could we or other organisms be able to do that? So why can't life usually survive in space? There's no air, so there's very little oxygen, and a lot of organisms require oxygen to live, and those that can't usually require other things that are found in the air. It's too cold for a lot of organisms, but also in some parts much too hot for most things to live. And there's a lot of radiation, which can cause harm and damage, as we'll see later, to living things. And it's also very dark, and a lot of different organisms require light to live. So in general, there's a few things that are required to sustain life. So you need a way to make energy. You need a way to sense environmental stimuli. And you need a way to handle environmental stress or change. So that when you're in adverse conditions, you don't just immediately die. So a way to make energy Again, out in space, a lot of organisms require light or oxygen or carbon dioxide in order to make their energy, and those things aren't usually out in space. You need a way to sense environmental stimuli, which doesn't necessarily, being in space doesn't necessarily remove those things. Those would be intrinsic to the organism. But you have a lot of, like I said, heat or cold or radiation that can damage these systems. And you also need a way to handle environmental stress or change. Again, you are in a stressful environment. The organism needs a way to combat all of those things that are out there in space that are not a comfy place for these things to live. So, with all of those things going against them, can bacteria survive in space? So, there's actually an organism called Deinococcus radiodurans. These bacteria are extremophiles, so they can survive cold, dehydration, vacuums, acid, and radiation. So they can survive 500,000 rad. A Google search told me that humans can only survive about 400 to 1,000, and these things are at 500,000. So Deinococcus radiodurans usually forms these tetrad structures on the left. So 4 living cells will group together to kind of share resources or help to protect each other. And then a lot of times as well, they can form these multimeric tetrad structures over on the right, so they will aggregate and clump together. And another cool thing about these is that each one, so if you look at the left, there are 4 cells, and each one is an individual organism. Each individual organism contains 4 copies of its DNA. So humans contain 1 copy of their DNA in each of their cells, and these bacteria contain 4. And during replication, or when they're trying to split into 2 different cells, they can carry as many as 10 copies of their genes. So there was a study where they dried out some Deinococcus radiodurans cells and sent them to space to see if they could survive the space environment, survive the radiation out there. And it was actually found that they can survive 3 years in space. So what they did was they used these boxes and they would stack plates in them, and they have different like sizes of cell pellets inside of these plates, and they shipped it out enough to where they could take a sample after 1 year, 2 years, 3 years. And so after 3 years, they checked the survival of these different dried out cell pellets. So they would resuspend them in liquid and put them out on a plate and see if they were still alive and still growing. And they found that depending on how thick the cell pellets were, depending on how thick the cell pellets were, showed survival. So 1 micrometer thick cell pellets, nothing was alive. And then 100 micrometer cell pellets, you had a little bit of survival. But then after 500 and thicker, there's no difference. And there was a really high survival rate in all of these pellets. And so the thought is that since they form those multimeric structures and they're all, sticking together, the outer layers of the bacteria of the pellet were absorbing all of the radiation, and they died first to protect the ones that are further inside the pellet. And when I was talking about this with Brad, he asked me about tardigrades that I hadn't really heard about before, so I went to go look and see. He asked me, are these bacteria cooler than tardigrades? And tardigrades can only survive 10 days in space. And also, they're animals, they're not bacteria. So, Deinococcus radiodurans can survive radiation for at least 3 years in space. So what happens when cells are irradiated? You get DNA damage. There are a couple of different things that can happen to DNA. You can get single-strand breaks, which are the easiest to recover from. You can also get double-strand breaks, which are very hard to recover from and are often lethal. And you get thymine dimers, where different amino acids, different nucleic acids in your DNA will stick together. And that's not good for when your cells, try to replicate or further survive. So bacteria have been irradiated, but they're still living, so there must be a way to fix the damage that's happened to the DNA, right? And there are a couple of different ways. So there's this little one that can be used for the thymine dimers. So you would cut on either side of, your cells, your enzymes would cut on either side of the dimer, remove the section of damaged DNA, and then normal replication machinery would then make a copy of the DNA that's still there, and then you get probably okay again DNA at the end of it. But what happens if you get a single or double strand break? Or what happens if you get a double strand break? Those things that are a lot more dangerous. So there are kind of two ways of repairing those. You would get non-homologous end joining, which is really fast. So if your DNA is trying to recover in a hurry, it would use this one. But it just takes the broken ends and sticks them back together. There's no thought for, am I gonna retain fully functioning DNA or not? It just sticks the things that are broken back together. And then there's homologous recombination, which is a lot better for maintaining normal gene function. The one that I want to emphasize at this point is the double holiday junction. So your DNA, if there's another existing copy of the DNA somewhere where it can match up, I have ATA here, I have ATA there, the good DNA will open up, and then a copy can be made for both of those strands in the double strand break. And then there's some cutting involved to get the strands rearranged, and then you end up with DNA that shouldn't be mutated and should be still fully functioning. So cells do have a way to recover from this kind of damage. However, not every cell can do this with the same efficiency. So how does Deinococcus radiodurans survive that much radiation? And they use a different kind of homologous recombination. So the one that I talked about is on the right of this figure. They use something called synthesis-dependent strand annealing. So you can see the difference is right, the fourth part down in the figure. So instead of when the good DNA opens and making two different copies with your two different strands, you just copy one, and then you don't have to do any extra cutting or rearranging at all. And you can use that now good strand to fill in the gap on the other one, and you end up with something that required a lot less steps to create. But it's not the only organism that does that, so what gives? Deinococcus radiodurans also has little bitty proteome shields, like very tiny, proteins that can protect against damage caused by reactive oxygen species. They're kind of like antioxidants. They also have increased catalase and superoxide dismutase. So those are enzymes that also work to neutralize the effects of reactive oxygen species. So reactive oxygen species are like hydrogen peroxide or free radicals that can bind to different proteins or DNA and also cause damage. And radiation reacting with water molecules in the cell produces a lot of this ROS, and that's where a lot of the damage comes from, besides direct action on DNA. They also have altered metabolic pathways to bypass steps in which ROS are produced, so they naturally just contain a lot less damaging things in their cells than other organisms. And they also have increased proteolytic activity following radiation damage. So after they have been exposed to radiation, they know they have a better sensing mechanism for, okay, this protein is damaged. It needs to be cut or killed and then can be recycled so that we can more efficiently use our resources after being exposed to an adverse condition. So that's how Deinococcus radiodurans does it. But can other organisms become radiation resistant? So the Cox and Batista labs, Dr. Batista was at LSU. I think he retired, but they used directed evolution to create a strain of E. coli that is resistant to radiation. So you grow out a culture of E. coli, expose it to enough radiation to kill 99% of them. And then those that survived are allowed to grow in, better conditions. And then those are exposed to more radiation until a small percentage survive, and so on and so forth. And they found that a lot of the common mutations that were found in E. coli were in DNA repair, DNA replication, cell division, and proteolysis. So all of those things that Deinococcus radiodurans uses to overcome radiation damage. And there was also another study that showed that when you open up a Deinococcus radiodurans cell and you open up an E. coli cell and you kind of mix the parts together, the proteome shields, those little tiny proteins, were actually able to shield E. coli proteins from damage to radiation. So other organisms could possibly be forced to evolve to overcome radiation damage if that were a necessity. It might take a while because bacteria grow quickly, and organisms that don't grow as quickly, it would take a couple of generations, hundreds of years, or maybe some kind of genetic modification could go on if we, needed to acquire that skill in a hurry. Who knows? Lots of possibilities. And that's all I have for you guys. Thanks.
All right, so just a reminder, if you guys have any questions for our speaker, please go to the mic in the back, and that's where you can ask your question. And yeah, so if you have questions, you're welcome to start.
Go ahead. No, I'm not asking. Just.
Can you hear me?
Yeah.
Can you hear?
Yes.
Yeah, she can.
Okay.
She can hear you. Ask your question.
What's your favorite Pokemon?
Okay, so the question was, what's my favorite Pokemon? I'm gonna say Ralts from Pokemon Sapphire and Ruby. The one that looks like a little girl with the green hair.
All right, any other questions?
Can you hear me, Erin?
Yes.
All right. So my question is, you called me out and pointed out the tardigrade stuff. Sorry. But does bacteria have some advantage being bacteria as opposed to an animal with the radiation resistance?
Do bacteria have some kind of advantage over animals when it comes to radiation resistance? So I know that bacteria are usually more resistant than larger animals or than eukaryotes. I don't quite know the reason. I know that in the sense that it's harder to break something if it has less moving parts than another thing. So bacteria are less advanced. They have less moving parts. Their DNA replication or recovery requires less proteins to do it. That might be why.
Question as well. Have there been identified other bacteria and fungi unique to space, such as on aircraft, that we identify, and also their composition? Are they the same elements that we're familiar with, and nucleosomes like we're familiar with, or anything unique?
So the question is, are there other bacteria or fungi that are found on aircraft? And do they have unique what was it again?
Oh, got it. Unique composition, such as nucleosomes, amino acids, different ideas of panspermia, or anything unique that we find in these new bacteria or fungi?
Do they have anything unique to them? That question I am not sure about. I know that quite a few of the Deinococcus genus lives up there. I know that they, in my reading to prepare for this, they've found Streptococcus that can like be carried on to the spaceships and continue to survive in like the ventilation systems. Yeah, I know that they can like there are different species that can survive on things, but not like out in the middle of space. But I don't know if they appear to be any different than their counterparts that have not left the Earth.
Hello, I have a question. Do you know if there are any bacteria that form spores that survive in space?
Are there any bacteria that form spores that survive in space? I am also not sure about that.
Okay, we do have a question. We have a few online, but I'm going to read one for now. Is there a benefit to having bacteria survive in space?
Is there a benefit to having bacteria survive in space? So there are a lot of bacteria that are beneficial to us. I'm not sure what the benefits would be for having bacteria survive just out floating in space. But if one were to try to maybe colonize or form a civilization elsewhere, not on Earth, it would be beneficial if bacteria could come with us and help with that. Like there are bacteria that fix nitrogen and allow plants to grow, or bacteria that can eat up or neutralize waste or pollution that's, dumped somewhere. There are other things that are beneficial about bacteria, but that would be some of them.
And my question relates to the protein that you mentioned earlier. Once we figure out the composition of a protein, is that difficult for us to make ourselves, or just to harvest from the bacteria that we figured it out from?
Once we find out the composition of a protein, would it be difficult to make ourselves or to harvest? Probably making it synthetically might not be too difficult to do. But the question would be, does it act in the exact same way? Does it still fold properly to be functional? And as for like harvesting it, protein purification in the way that it would need to be done natively there is a very long process, and these things are very small. So one could try that way. But then again, trying to put that synthetically made or isolated protein into another system would require testing to see if it's doing what it's actually supposed to be doing. Because not all bacteria remain functional when they're put in not all proteins remain functional when they're put into another organism.
All right, we do have another online question. Do the 4 cells share their genome in this particular kind of bacteria, or do they share other proteins and such when something is damaged?
Do the 4 bacteria share their genome or share proteins? So in times of stress, bacteria do have a way to kind of share resources with neighboring bacteria. I'm not sure if they would be able to like share their genetic material in a timely enough manner to like piggyback repair off of another cell's version of DNA, but I think certainly that they could try to share their resources among themselves, or like with each other.
In your discussion about the forced evolution or the directed evolution for E. coli, what are your thoughts on potential risks and or safeguards for creating an E. coli that could survive beyond our methods to keep ourselves protected?
So E. coli specifically, you can direct it in a way that would make it more resistant to radiation. However, in doing so, you don't inherently give it a better chance of survival in other environments. So just because an evolved E. coli could survive more radiation, that doesn't necessarily make it more resistant to things like heat or pressure. So it might be worrisome if if in obtaining radiation resistance, it obtains more resistance to that. But I don't think that is an issue for an experiment like this.
All right. Thank you so much, Erin, for your very interesting talk. You have a lot of accolades coming from our online audience. And our in-person audience, let's give her a round of applause, even though she can't hear us. All right, so next up is going to be our intermission. So during our intermission, we're going to have trivia. And so I promised you some cool prizes, so I'm going to read a little bit about them. So we have some cool prizes today, sponsored by our friends at Science Socks today. They make really cool science-themed things. They have a lot of cool holiday gifts, including a whole collection based off of the James Webb Telescope. And make sure to check out their website, which is www.sciencesocks.co, not .com.co. So if you would like to participate in our trivia, you have some chances to win some cool stuff. It has been shown in our slides. And also, we do have a tip war going on, and we will have some volunteers coming around with our tip jars. Our tip war this month is, what is the best way to cook a turkey on reentry or off a launch pad? So choose your favorite way to cook a turkey. And with that, have fun with our trivia, and we'll be back shortly. All right, everybody. Hopefully you had fun guessing your constellations, and hopefully you learned something about the constellations. We will go over the answers after our next talk, so make sure you stick around. And same with your raffle ticket. Make sure you hold on to that raffle ticket. If you have already lost it, you're welcome to grab another one, but make sure you hold on to that. We will be doing the raffle at the end as well. All right, so our next talk is by our very own Brad Munson. He is a 6-year graduate student in the Physics and Astronomy department. His research is in computational astrophysics, simulating stellar binaries. He plays piano, but it's been a while, Nintendo Switch games, and PC games, and he's finally perfected his pina colada recipe. So give it up for Brad.
Thank you, Ashley, for that introduction. So how are you guys doing tonight? We really appreciate you coming out here in the cold and the rain. This is fantastic turnout. So, you may recognize me. I was the MC, but, you know, we need new blood. I'm older than I look. I need to get out of here soon. So now I'm just a speaker. So I'm going to talk to you about drones in space. And your first question might be, what do you mean by drones? Drones is a general term for an unmanned aerial aircraft, yeah. Oh dear. Well, I promise it was working. All right, Alex, I'm gonna have to cue you over there. All right, so a little bit of a disclaimer. By drones, what I actually mean are rotorcraft, which means an aerial or an aircraft that has its lift only powered by the propellers. It doesn't have wings. So the military has drones that look like little airplanes, but there's no people inside. They're scary. You can get RC drones. They have propellers, but what generates the lift are the wings itself, not the propeller. I'm talking about things like these, or even things like helicopters, where the propellers actually generate the lift. Yeah, I'm sorry, Alex. This isn't working at all. You can go to the next one. So when I say that, it means that we need air, right, to generate lift. Propellers need air in order to push themselves up off the ground and fly. So I don't actually mean drones in space. That title's just catchier. What I mean is rotorcraft on other planets. But when you give a talk, you have to appease the person who makes the slides or the posters. Thank you, Allie. And drones in space is catchier, shorter, and nicer. But rotorcrafts on other planets. So here we go. Next slide. So rotorcrafts today. All right, Alex, I'm going to go one by one. Every time I say something, just go to the next slide. All right, we've got small ones. We've got big ones. We've got ones you can ride in, but thankfully they're not available for commercial purchase. If you think Baton Rouge traffic is bad now, if you had those flying around, forget it. All right, next one. We've got ones in the workforce, in the construction workforce, in order to take pictures and survey construction sites so that construction workers don't have to take the risk and go up to those high heights, those scary heights, and take all that risk of falling and, you know. So drones take really good pictures. They're very steady, and they do a good job at mitigating that risk. Okay, next, we've got them in the agriculture business too. They spray your crops, so we don't have to hire someone in a biplane to go back and forth and spray your crops with some pesticide or whatever you have. It's an automated path, and it saves the farmers a lot of money. Next, we even have drones to capture other drones. This is a little bit ironic, but with all the drones out there in the world available for commercial purchase, they are running rampant. It's like a pest. So we have other drones that capture those drones. It's ironic, I know, it works. All right, next. So my first drone I want to tell you about is actually a helicopter. It has already flown, it has already completed its mission, but I made this talk, well, I made half this talk like 3 years ago. So the first drone I'm going to talk to you about is on the Perseverance rover. And if you're a longtime AOT enjoyer, you might recognize this picture from our virtual days. This is from our BattleBots setting of Curiosity, here armed with circular buzzsaw and flamethrower, versus Perseverance, which has a laser beam, which is actually a camera, but Photoshop and then a hammer still attached to its human hand. Now, that's cool and all, but what is Perseverance? Next slide. So Perseverance was a rover we launched on July 30th of 2020, and it landed on February 18th of 2021. It's a long drive. And its mission was to determine if life has ever existed on Mars before. It's going to characterize the geology and the climate in order to prepare for eventual human exploration. That's far, far in the future, maybe. I don't know. Elon Musk is really doing stuff, well, not all good. So yeah, we're going to prepare for human exploration eventually. But again, that's still not what I'm talking about. I'm talking about drones in space. So we'll go to the next slide. Oops. Oh my God, it worked. All right, so on the belly of that rover on Perseverance is Ingenuity. Ingenuity is the helicopter. So this is the first drone I'm going to talk about. It's not working anymore, Alex. I need you to go to the, thank you. So Ingenuity is a proof of concept mission. It's not going to do actual science on Mars, which is a little disappointing, but we've never taken flight on another planet. So we need this proof of concept mission, which is an engineering mission, really. And it's going to prove that powered flight on another planet is feasible, and not only feasible, but maybe even a good idea. And I'll talk about why maybe it's a good idea in a minute. But first things first, the biggest challenge is we need autonomous operations, right? This makes sense. Mars is a long ways away. DJI, if you've heard of that drone company, they're really popular. They've got expensive and very useful drones. They brag about having drones that have a range of 5 miles away. Mars is much further away. So the communication time from Earth to Mars, at minimum, when they are the closest together, is 187 seconds. The flight time of the helicopter is 90 seconds. So you can't control this with the remote control. By the time a signal reaches the helicopter, it will fall out of the sky because the battery died. Now, that's the first challenge. The second challenge is the atmosphere on Mars, as you might know, is much thinner than that on Earth. It's about 1% as dense. So that means it takes a lot more work to generate the same amount of thrust and take flight. Although we do have a little bit of an easier time because the surface gravity is only about 1/3 as strong. Now, how do we actually generate thrust with the atmosphere being so thin? Well, Ingenuity has a few ideas. So you see here are 2 propellers. They're coaxial, so they're on the same axis, and they counter-rotate. They spin in opposite directions, and that's important. Maybe I'll talk about that later. And you notice that these propellers, you might notice that they are proportionally much longer than propellers you would see on a standard helicopter on Earth. And that's because they need to push more air downward because there's less air available. Not only do they have longer propellers, the propellers spin much, much faster. So they're made out of a very rigid material. It's this carbon fiber foam core, and they spin at about 2,400 rotations per minute. To give you context, a normal helicopter on Earth spins at about 500 rotations per minute. So this is about 5 times faster. So much, much faster, and that's how we're able to accomplish flight on Mars. It's a much longer propeller, and it spins much faster. We're able to push more air down, even though there's less air available. So some other features of the helicopter. It's got antennas, because it's going to take nice pictures and send them back to the rover, and the rover is going to send them back to the orbiter, and the orbiter is going to send them back to Earth. It's not direct, but it's what we can do. It's got the blades, which I just talked about. It's got a solar panel, which are going to charge the batteries, which are going to power the flight and the cameras. As far as the cameras, the helicopter has 2 cameras. It has a low-resolution black and white camera, which are going to take very low-res images of the ground as it's flying to get velocity estimates. It's going to measure stationary rocks and features on the land, see how fast they go past the frame of view, and it's going to estimate how fast it's going because there's no GPS on Mars. Surprise. And then it's got a color camera, a very high-resolution color camera to send pictures back to Earth because we all know you're not doing real science unless there's good pictures involved. It's got an avionics body, so inside this foil-looking body here are all the sensors and the cameras and the flight equipment. And the body itself is protected against radiation and cold temperatures. So the temperatures get down to minus 130 degrees Fahrenheit. And of course, there's very harsh radiation on Mars with this thin atmosphere. It doesn't block a lot of the incoming radiation from the sun. So it needs to protect all of its electronics from that stuff. And there's a lot of thought that needs to go into this helicopter. So let's move on to the next slide. So the first challenge for the helicopter is to take flight. And its very first flight, it's very impressive, not because the flight itself was impressive, but because it is the first flight ever done on an extraterrestrial body. So if we can play that video, it doesn't look impressive. It goes straight up, it hovers for a little bit, and then it comes straight down. I think that deserves a round of applause, right? Well, NASA would think so too, because again, the flight didn't look that impressive, but this is the first step you have to make to do powered flight on other planets. This is a very important step. We need to take small steps at a time, because if you screw up now, it takes a long time to get another helicopter up there. All right, next slide. So that's not the only flight it took. It has to make more progress than that. So it made in total 33 flights. On one of the flights, it took this image of the back shell from the Ingenuity lander and the parachute. And so this was taken from about 26 feet up in the air, which was much higher than the 10 feet of its first flight. So as it takes more and more flights, it continues to push the limits. It moves higher and higher, it moves faster and faster, and it goes for a longer distance. All right, next slide. Oh, did I do that? I don't know. So again, 33 flights between April of 2021 and September of 2022. And in total, it had about 59 total minutes of flight time. Every flight lasts about 90 seconds, like I said before. It's not very long, but it's what we can do. It went a total of 24,000 feet over all of its flights. And its peak altitude it ever reached was 39 feet and peak speed 12.3 miles per hour. Now, that speed doesn't sound impressive compared to things we can do on Earth. My Honda Accord can, I don't know, I haven't maxed it out yet. But compared to rovers on Mars, that's pretty quick. So what can we do with this? This is, again, a proof of concept mission. So we need to show what kind of missions we're striving for. So let me introduce you to the next slide, which is New Frontiers for Dragonfly. So New Frontiers is a series of missions set out by NASA in order to explore the solar system. New Frontiers 4, called Dragonfly, is set to launch in 2027. So we're still talking in the future. When I first gave this talk, it was 2026. Fingers crossed it doesn't keep moving forward like some other missions we know about. 2034 is when it's going to arrive on Saturn's biggest moon, Titan. So Titan is a very cool object for an origin of life study. I'll talk more about that in a minute. But for now, we'll move on to the next slide and talk about the difference between a helicopter and a multi-rotorcraft vehicle. So this is important because, of course, our proof of concept mission was a helicopter. That picture I just showed you was a quadcopter. They're different, and those differences are important for this mission. So a helicopter has an adjustable pitch. You see this propeller right here? That means that it's allowed to wobble and tilt. And by it wobbling and tilting is what allows it to move side to side, forward, backwards, and do all of those fancy maneuvers. But that actually makes it more energy efficient and mechanically stable, meaning if you had none of the avionics on board, none of the computer chips or fancy technology to keep you upright, all on its own, it would more or less remain stable and not kill anyone. However, it's very mechanically complicated. As you can imagine, allowing it to tilt in all 360 degrees requires a lot of joints. And so there's a lot of single point failures. If any one of these propellers, the main one or this tail one, break down, then you can't take flight. Does anyone, by the way, this is an open question, so if anyone can answer, does anyone know what that rear propeller is for? Yeah? That's right. That's right. So if you have ever seen like war movies where they shoot a helicopter down, the tail comes off and the helicopter comes spiraling down and crashes, it's horrible. But that's true. That's what would happen because the helicopter is forcing the propeller to rotate, and in turn, the propeller forces the helicopter to rotate the other way. If we allowed that to happen, it would take awful pictures. It would be moving all the time, and everyone on board would be sick to their stomachs. So we put a little propeller here to counter-rotate the body of the helicopter so that it remains facing the same direction. A quadcopter, however, or any multi-rotor craft, is a fixed pitch vehicle, meaning that the propellers aren't allowed to tilt and wobble and whatnot. In order to move forward, backward, side to side, the rotors that are facing the direction you want to move rotate slower, so that side of the vehicle drops, and the ones in the back move faster, so it moves forward. Okay, so it's a little more simple because there's not as many joints involved, but it's not mechanically stable, meaning if you didn't have the computer chips on board, this thing would take off and flip over almost every single time. It just takes a slight perturbation to flip it over. However, it's mechanically simple. This picture of a drone, you might be able to recognize. These are just popsicle sticks, 4 motors, 4 propellers, a circuit board, and a battery, and it will fly more or less stable. In fact, next slide, I'm sorry for this in advance. Please play it. There is okay, so we've heard that astronomers are weird. We're not the weirdest ones out there. Someone taxidermied an ostrich, set it up to a bunch of propellers, and now ostriches can fly. All right, I don't think we need to see any more of that. Anyway, back to the mission. Dragonfly. So why do we pick Titan? This is an origin of life study. We picked Titan because it has a very carbon-rich chemistry. So there's lots of water ice on the surface. Titan is very cold. You thought it was cold here in Baton Rouge right now. Titan is minus 290 degrees Fahrenheit on average. It's what, like 40 degrees here? 55? Guys. You don't need the coats, the heavy coats. We've also got liquid oceans underneath the surface. So kind of like the Earth has molten rock. It's the same but different. It's also the only other place in the solar system other than Earth that has liquid rivers, lakes, and oceans, except on Earth, they're all made out of water, right? We know this. On Titan, they're all made out of methane, so the same but different. It's also the only moon to have a substantial atmosphere. In fact, Titan has an atmosphere that is 4 times more dense than Earth's. You remember Mars's problem? It had a very thin atmosphere, and that made flight difficult. So this one's even more dense than Earth's, so that makes flight easier. In fact, the moon is also only about 1/10 the mass of Earth, and so that makes flight even easier. The flight power you get on Titan is about 40 times more. So flight is not only feasible here, but probably a really good idea. We've also got 13 years of Cassini data, a flyby mission around Saturn. It also took a bunch of pictures of Titan, and we were able to identify some interesting looking locations and safe landing sites and safe times to land at those sites based on the weather patterns for the drone. Another fun fact about Titan, so I mentioned it has lakes, rivers, and oceans of methane. It also has an entire hydrological cycle of methane. So it rains, it snows on Earth, water, on Titan, methane. It's the same but different and probably worse. Next slide. So here's the design of Dragonfly. It looks like a quadcopter being 4 propellers, but it's actually an octocopter. Although it has 4 axles, it has 8 propellers. It has 2 propellers on each axle. So that makes it technically an octocopter, but it looks like a quadcopter. Not really important. It's also got this high gain antenna. It looks like a dinner plate. It's not very aerodynamic, so it's attached to a gimbal so it can raise up and down for when it flies and when it's on the ground. It has 2 cameras. Oh, whoops, I missed one. It's got an MMRTG, which is its power source. Now, does anyone know what that stands for? Multi-mission radioisotope thermoelectric generator. So yeah, very close. It's also got 2 cameras. It's got a panoramic camera to identify good landing sites and a microscopic camera to look at its samples. And how does it get its samples? It's got 2 mechanisms here. It's got a drilling mechanism to ground out pieces of the moon. And then it's got a sample acquisition system, which is a fancy way to say it's got a vacuum. So it vacuums up those samples from the moon, and it analyzes those samples with a few scientific pieces of equipment. Can we go to the next slide? I really wish the clicker just worked. So you can see here all the names are appropriately named like dragons. It's got DRAMS, which is the mass spectrometer, and it's used to identify the chemical components relevant for life in both the atmosphere, so gas samples, and in the dust that it collects, the geological samples, so the Earth samples, or I guess moon samples. It's got DRAGONS, which is the gamma ray neutron spectrometer, which identifies the surface composition underneath the lander. It's got DRAGMET, which is going to study the weather and the seismology on the moon. And then it's got the Dragon Cams, which I just talked about, to study the terrain and identify good landing sites for the future. Next slide. So how is this thing going to land? Like any good NASA mission, it has to land in style. Let's play the movie. So it's going to descend in the parachute, and then it's going to drop from the parachute mid-descent in free fall and start its flight mid-free fall. That's the style. So that means that the parachute doesn't have to be precise when we're picking a location, because the drone is just going to fly to where it needs to go anyway. It saves us a little bit of trouble. And so once it lands on Titan, this is a slow movie. It's going to raise the antenna, and it's going to establish communication back to Earth and let us know that it made it to Titan safe. It's ready to do some science. And so it's going to start, take off, and go do its science. So what does that science look like? Next slide. So the first thing we're going to talk about is leapfrog reconnaissance, and this is how it's going to mitigate flipping over. Now, it's important to mitigate flipping over because there's nobody on Titan to upright it. Not only because Titan is so far away, this drone is about 1,200 pounds. It's like the size of a small car. It's very big. Again, flight is very reasonable, so we can put lots of weight on this thing. So it's going to do leapfrog reconnaissance, which means we have sites A and B here identified from the Cassini data that we looked at before. When it arrives by parachute, it's going to land at Site A, establish communication, and when it goes off to do science, it's going to go past Site B, which was identified by Cassini, and go to Site C and look for a safe landing spot, one where it probably won't flip over or have anything catastrophic happen, because again, if something happens where the drone can't take off again, that's mission failure, and that's a waste of $850 million. So then, after it identifies a safe landing space, it's going to come back and arrive to Site B and do its science. It's going to crush up some moon, suck it up, and analyze it. And then after Site B, it'll look for a safe Site D, and then come back, land at C, do more science. You know, you get the picture. All right, next slide. So how is it going to do that science? So here's kind of the power cycle that we're looking at. It's important to remember that Titan has an 8 Earth day. So on the x-axis here, we've got Earth days. On the y-axis here, we've got on the red curve the elevation of the Earth in radians. That doesn't make sense, or degrees. And the battery consumption in percent. So the important thing is this is daytime on Titan when the side that the drone is on is facing the Earth and the sun, so we can communicate with the drone. And then this is nighttime. So here's the power cycle. It's going to start the day at a full charge. It's going to communicate with Earth, tell us it's ready to go, and then it's going to charge up as we make some decisions. Then it's going to take off and do that leapfrog reconnaissance we just talked about. And then it's going to arrive at its landing site where it's going to do some science. It's going to crush up some moon. It's going to vacuum it up and do some analysis. And then It's going to do this kind of periodically until nighttime. Once the moon faces away from Earth, we can't communicate with it. So this is an opportune time for the drone to start recharging using that radioisotope thermoelectric generator. It's basically these they're radioactive spheres that decay and generate heat and power over some time. Now, they're really reliable. These are on the Voyager missions, by the way, and we know how long those have been going. Those have been in your textbooks, your history textbooks even, for quite some time. So over the course of time, that power source will charge the batteries over 8 days. It's a very low power output, but it's got a long time to recharge. And occasionally during the nighttime, I might do more science, crush up some moon, vacuum it up, analyze it, whatever. And then it has a full battery for the next day, and it repeats the cycle. Next slide. So the mission goal of this, so that's a day-to-day task, but the ultimate goal is it's going to land in a Shangri-La dune fields, which are these clear fields we saw from the Cassini data. And it's going to leapfrog 8 kilometers at a time. Again, no need to risk landing on a site that's not deemed safe because of our leapfrog reconnaissance. And with every progressing site, it's going to collect more and more data, do more and more analysis, and give us more and more information about Titan. So it'll end its mission in the Selk Impact Crater, which is a very geologically young crater. It looks like it's formed not that long ago on a geological timescale. And it has evidence of liquid water and all the ingredients for life that we could need: a rich carbon chemistry, liquid water, and maybe it'll tell us something about how life originates on Titan, and we can compare that to what we know here on Earth. And that's interesting, and it even kind of relates back to Erin's talk. I have to call her out now that she called me out about tardigrades. But it's very interesting, and this type of mission with such a wide range is only possible with drones going to other planets, or rotorcrafts going to other planets. Now, why? Because think about this. The Mars rovers, Curiosity went a total of 17.5 miles over its whole life. That's not a lot. Like, that's my drive to wherever I want to go sometimes. So it has to do a lot of science in a limited space. Now, Perseverance, it hasn't been around as long, but it's still only gone 5 miles over its life. Any guesses as to how many miles we plan to cover with Dragonfly? Sure. How many? I still didn't hear. 100? A few hundred. Close. But less. It's 108 miles. If you said 100, I would have given you the right. I just said 100. But 108 miles. That is huge compared to these rovers because it's not subject to the terrain that it has to crawl across. It just flies right over it. And it just picks these good-looking landing sites and lands right in them and does its science. So that's really all I have for you guys. I thank you for listening. And again, thank you for coming out here during the rain and the cold. We really appreciate it. And I hope you appreciate quadcopters, rotorcrafts on other planets. Thank you.
All right, another round of questions. All right, we do have a question online, so I'll start with that one. Is the carbon fiber foam core the same material the Starship heat shield is made of?
I have no idea.
Short and concise.
You said 108 miles. I'm just not sure if you mean that's the physical limit that can go as the crow flies, or if that's the reasonable limit that's expected from the mission, from the landing point.
So that's distance and not displacement. So that's all the added distance of all of its paths, not the distance from start to end. Oh, sorry. The question was, what does 108 miles mean? Is it from start to end, or is it the total distance that the drone flies?
Any worries you have of the heat in the RTG melting the surface ice and causing problems that way with the recharge cycles?
So is there any worry with the heat from the MMRTG melting the ice? And, sorry? Yeah, and so I don't think so for two reasons. One, again, it's minus 290 degrees Fahrenheit on Titan, and the atmosphere is very thick. It's going to take a lot of heat to penetrate that insulation just from the atmosphere alone. And it generates a total of 100 watts of energy at the beginning of its mission. Of course, it decays so that power generation becomes less and less over time. And so I don't say this with complete confidence, but I don't believe that the heat generated is going to be enough to melt the ice, which effectively acts as rock on Earth. Again, minus 290 degrees Fahrenheit. This ice has not been liquid in its life. I mean, it has, but let's be real. Yes, Jude. What's my favorite? Okay. What's my favorite Pokemon? Number 151, Mew. I like it because it's like somehow the ancestor to all Pokemon and it can learn every move. It's awesome. Do you have another? What if you light a match on Titan with all that methane? Would it catch fire? I wouldn't want to find out. I wonder if the match would strike, though, with the lack of oxygen. I don't know that it would. Yes? Yeah, that's true. So he made a comment, which is a really good point, that because it is so cold on the planet, the craft is really well insulated. We don't know the specific details on this yet because, again, this is in 2027. The craft hasn't been built yet. But it does have to remain a really good thermal insulation, meaning that just as it has to keep the cold out, it has to keep the heat in. And so that means the heat won't necessarily get a chance to melt the ice outside of the craft. Yeah, can you go back to the leapfrog reconnaissance? So yeah, the plan is you never land at a site you haven't already deemed as safe. So when the aircraft first arrives, it has deemed two sites as safe, sites A and B. That's from the 13 years of Cassini data we took. And then it'll fly over B. It already knows that B is safe. It's going to look for a future site that's safe, site C. And so it's going to go back to B. It was already determined to be safe. And then from B, after it's done doing its science, grinding up some moon, vacuuming it up, and analyzing it, it's going to go past C, which was determined to be safe from the last time. It's going to look for site D, see if it's safe, and then it's going to land at site C. Yes? Yeah, so does Titan have two? You mean to that would make the leapfrog kind of worthless? Well, just more difficult or yeah. I'm not a very technical person, but the idea that like if something goes wrong with it, like it tips over, like you just can't fix it, that sounds terrifying. Yeah, it is terrifying, and NASA has to deal with that a lot. You should look at some previous missions. But yeah, so the question is, do the weather systems on Titan make it more risky to pick out those landing sites? Because essentially, what is deemed safe today might not be safe tomorrow because some storm of liquid methane rolls through and knocks your... Is that more or less what you're asking? Yeah. So, and that's part of the reason with the Cassini data, we're also picking a good time period to take these flights where there's very little storms. We're not going to be able to predict the day-to-day as we're flying out there. Again, this is launch in 2027 and it arrives in 2034. We have no idea what the weather's going to look like that many years in advance. But We do try to pick a time frame where the storms are minimal and in an area where those storms are minimal. Sure.
Another question from our online audience. What limits the mission length? Is this how often it is likely to flip or power source, like its power source duration?
Yeah, so the mission length, I think it's usually just determined by funding. But again, it's not really the power source necessarily, because again, the Voyager aircrafts are still going strong, right? They just exited the solar system, what, like 4 years ago, maybe? 4 or 5? And they're powered by the same device. And so how long have they been going? Or I guess the question is, how much longer have they been going than their predicted mission time? I don't know the answer to that question. But the possibility is very real that this mission could extend the predicted time it would take. Yes? How would we receive data from the Dragonfly? So it's got the, can we go back to the design of Dragonfly? Back, that one. So the high gain antenna. So it doesn't look like much, but remember, it's actually very big. This whole thing is the size of a small car, so that's not just a dinner plate, that is like a whole buffet tray. That is the antenna that's going to send the signal back to Earth. So it's going to send pictures to us, it's going to send us the results of its analysis of those samples that it takes. That'll send all of our data back. Yes? This one a direct signal to us then? Yes. It's not bouncing off yeah, no. It's direct from Titan to Earth.
All right, last question. Go for it.
What's the recipe for the perfect pina colada?
Oh my God. All right, you ready? You got your pen and paper? So, I don't know if I'm going to offend the bartender or not when I give this recipe for a pina colada. I don't know how accurate it is, but I like it. I use 1.5 ounces of a Caribbean silver rum, 1/2 ounce of gold rum, or aged rum, 3.5 to 5 ounces of pineapple juice, depending on how sweet you want it, and then 2 ounces of coconut cream, and a maraschino cherry. If you use the maraschino cherry, don't get those like candy red ones. Get the Luxardo ones. The Italians do a really good job at cherries. Luxardo cherries are the best. Always get those. You'll notice a difference immediately. If you just taste one, you'll be like, this is what a real cherry tastes like.
All right, so let's give it up for Brad. All right, so next we're going to go ahead and go over our trivia answers, and then I'll announce the trivia winners. Give us 1 second. All right, so question 1. This constellation was named for a lady of Greek mythology who rescued Perseus. That is... Next slide. I don't have the clicker. Andromeda. Yep, Perseus did rescue her. All right, next slide. The mother of Andromeda, whose constellation forms the letter M or W, given how you look at it, it is Cassiopeia. The name is Latin for water carrier and is a part of the zodiac. That is Aquarius. All right, the largest of all constellations and is associated with Hercules. It is the Hydra. Represented by a ram who is associated with Jason the Argonaut, that is Aries. Home to the Northern Cross and is also a binary star system. That is Cygnus. The only zodiac constellation that doesn't represent a living creature. That is Libra. The smallest constellation in the zodiac. That is Capricorn. The second largest constellation and is the largest within the zodiac, which is Virgo. And last but not least, the two brightest stars in this constellation are Castor and Pollux. That is Gemini or the Gemini twins. All right, so we have two winners. Hopefully I don't pronounce your names wrong, so I apologize if I do. All right, our first winner, and when your name is called, go ahead and go up to our merch table and pick out your prize. We have Natalie Shepard. All right, and our second winner is Josh Gutierrez. Josh Gutierrez. Going once. Going twice. We need a backup. Pending, pending, pending. This could be you. We have Gabrielle King. Gabrielle King. Awesome. Congratulations. All right, so go ahead and get those raffle tickets out. Give everybody a second. All right, so if your number is called for the raffle, you'll also go up to our merch table and pick out your prize. All right, is everybody ready? All right, this one feels lucky. All right. 3, 0, 4, 8, 7, 4. That is 304874. Awesome, congratulations. Go on up to our merch table. All right, y'all, thank you so much for coming out on this cold and rainy night. I hope you guys have a great rest of your night and come and see us in December. Thank you.